The STL contains a number of template functions called algorithms that operate on containers. We'll cover some of the highlights here, but know that there are a lot more of them. This selection should provide enough examples for you to be able to use the rest of the library by referring to a reference source. The STL algorithms library represents a significant departure from other object-oriented languages. Most object-oriented languages use member functions defined in each individual class for common container tools. By virtue of C++'s template feature, these common functions are generalized in the C++ STL algorithms library, making them more consistent and ultimately easier to use. For example, to search a range of elements in a container, you would use the same search function no matter which type of container you're searching. Let's open up the algorithm.cpp file and take a look at how this works by copying it and pasting it into our working project. I'm going to double click on this, and I'm just going to minimize our project explorer off there on the left. And I'm going to run the compile and run. Scroll up to the top here and we'll take a look. We've got a number of include files up here. We have vector because we're using some vector containers. We have locale and algorithm. The algorithm header has the function declarations for all of the algorithms. There's a functor defined at the top here. Now, a functor is a function object, and we'll get back to this in a little while. We're going to use it. There is a little uppercase function that we'll also be using later. And then we come here to main. First thing we do in main is we're going to declare a couple of things here. We've got a string vector, we've got an integer vector, and we have iterators for both of those. The string vector is VS, and they're both initialized with initializer lists because I happen to think that's a very convenient feature from C++11. And then integer vector is called VI, and then there's VS iterator and VI iterator for the two iterators, and then there's a string which has the constant string in it, big light in sky slated to appear in east. So the first algorithm that we're going to look at is the count function. And so you'll notice we have our VS vector, and it has the words 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So one of those words is 7. Now push a couple of extra ones on there at lines 35 and 36. And then we're going to count the number of elements that match exactly the string 7 in the VS container. And so count takes two iterators, the beginning and the end of the container, or the beginning and the end of the range that you want to search. It doesn't have to actually be the beginning and the end of the container, but it needs two iterators to mark the beginning and the end of where to search, and then the object to search for. And it returns an integer number. And so we see here it says count VS7, and it found 3 of them because we pushed those 2 extra 7s onto the back, and now we're just going to pop them off the back again, and our string vector will be back to the way that it was. So that's count, and count is very simple, and it works with all kinds of containers. Next, we're going to call find, and we're going to find the number 7 in our integer vector. And on line 44, we give it a begin and end iterator, and then the object to search for, which in this case is an integer 7 because we're searching an integer vector, and it returns an iterator, so we're just assigning it to our integer vector iterator, VIIT, and we check and see if it matches vi.end, and if it does, it's not found, and if it doesn't, then it is found. I'm using the not equals to, so that our first if clause is found. And you'll notice that it found it, and it dereferences the iterator to print out the number 7 there. Scroll down here a little bit. This one is a lot of fun. This is called equal, and it checks a source range and a destination range. So it checks 2 ranges to see if they're equal. So the first range, this one is called equal, and it compares 2 ranges to see if they're exactly the same. The first argument is the beginning iterator of the first range, and the second argument is the ending iterator of the first range. And the third argument is just the beginning of the second range, and it assumes that they're exactly the same size range if it's checking for their being equal. And so we have one string, and basically what we're doing here, it's a little bit clever. we're comparing the first half of the string with the second half backwards. Our begin is the beginning of the string backwards, so it points at the end of the string with a reverse iterator. And so it's actually checking to see if this string is a palindrome or not, because you'll see p begin plus p size over 2 is going to be 3 because it's integer division. And so it's checking the first 3 letters of this 5-letter word to see if they're the same backwards. Our begin starts at the end and it's a reverse iterator, so it goes backwards. You'll notice here it says radar is a palindrome. A palindrome is anything that's spelled the same forwards and backwards. And so if I change this and I say Bill, which is not a palindrome, and I compile and run this, we'll scroll back up here and you see it says Bill is not a palindrome. If on the other hand, the longest palindrome I know is Lisa Bonet ate no basil. Lisabonetatenobasil. Lisa Bonet ate no basil. Save that. I know there's longer ones, but this one's fun anyway. And run it. And it says Lisa Bonet ate no basil is a palindrome. Again, what equal does is it checks 2 ranges to see if they're the same. And this is just a little trick to check if something is a palindrome using that equal function. So you can see that these STL algorithms are incredibly powerful and flexible, and you can do all kinds of cool and interesting things with them using the various features of the standard template library containers, things like the iterators and the reverse iterators and things like that. Next is search, which searches for one range within another range. So here you get a begin and end iterator for what I call the haystack, the bigger thing, and the begin and end range for what I call the needle, the smaller thing that's being searched for in the bigger thing. And it returns an iterator. So in this case, it's a string iterator, and we're calling it search iterator. And again, if it equals the end, then we didn't find it. If it doesn't equal the end, then we did. And here we're searching for, the string is big light and sky slated to appear in the east, and the search term is slated. And it found it at position 17. So it checks for a sequence within another sequence. Now we're going to get to COUNTIF, and COUNTIF is a whole lot of fun. Line this up here. So VS is our string vector, and you remember it has these 10 strings in it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What COUNTIF does is it counts the number of times a particular condition is true within a container. And what that condition is very, very flexible. The way COUNTIF works, it's like most of the if algorithms. It takes a pointer to a function called a unary predicate function as an argument. The function takes a container element as an argument and returns a Boolean true or false. The unary predicate function may be a function pointer, a functor, that is a function class, or a C++11 lambda function. Here we have this functor at the top. Just bear with me for a moment because this is actually a whole lot more fun than it looks like. Here we have a class called strHas. It checks to see if a string has a particular character in it. And so there's a character that I call needle and a string that I call haystack. We have a constructor that takes a character and initializes the needle to that character. And then we overload the function operator you see on line 16. It's declared on line 14 and it's defined on line 16. And it's a simple function that takes a string called haystack and it calls the string method find first of with needle and checks whether that equals the npos constant, which is defined inside of that string class. And so if it does, then it wasn't found, and if not, it was found. And so it returns that Boolean condition saying, I found this character in the haystack or I did not find this character in the haystack. So very simple. And this is called a functor because it's a class that overloads the function operator. And so it's a class that can be called as a function, but has all the power of a class. Store that little bit of information away, and we're going to come back down here and look at COUNTIF. And here we call COUNTIF on line 78. We have the beginning and ending iterators of our string vector. Remember, our string vector has 10 strings, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And it's going to run that functor on each one of those elements of the vector, and it's going to run the functor with the character s. So you see there, right here, this takes the class and it constructs a temporary object with that class, because we're just calling the constructor on the class, and we're passing the result of that constructor to the function call, and so that creates a temporary object and sends that object to the function, to countif. And so our result here is countif vs has s. The functor version, that's this one here, is 2. So it found 2 strings, this one and that one, that have an s in them. This version will work with all versions of C++, because functors in any version of C++ where you can overload a function object, which I believe is all versions of C++, this will work. And this is actually what functors were designed for, and this is actually how these if algorithms were designed to be used with functors. Starting in C++ 11, we have a new feature called lambda expressions. And this here is a lambda expression. So this is doing exactly the same thing, but instead of using a functor, it allows you to actually write the code in line right here where it's being used. And a lambda expression in C++ 11 is an inline function. And so I write this function right where it's being used, and it gets used right there in scope. And this is what they look like, and we'll cover them in more detail in the chapter on new C++ 11 features. But this feature using lambda expressions is actually really convenient for short little one-off functors like this one. So that's countif, and you see that our lambda version has exactly the same result because we're doing exactly the same thing. A for each algorithm calls a function for each element in a range of a container. In this example, I'm using a lambda, but of course you can use a functor or a function pointer. I'm showing the lambda because it puts the logic of the function right in the function call, and that's really convenient, especially for demonstrating. So here we have an example of for each, and we give it a beginning and an ending iterator with vs.begin and vs.end. Our little lambda function, all it does is it prints out using cout the uppercase of the string and a space. And so here's our result here. It's just printing out our string in uppercase. Very convenient. You can do all kinds of different things in that little function there, and it'll do it for each element of this range. Transform lets you do that same kind of a thing that you're doing in for each, but it allows you to do it and store your results. You can do this kind of thing with for each, but using transform, it gets very powerful and very flexible. So basically what transform does is it calls a function for each element of an input range, and it stores the results to each element of an output range. And the input and the output may be the same range. So here we have an example where we have an input range with begin and end iterators and an output range that begins at another iterator, and we're using our vi2 here. Here we're declaring another vector vi2, and we're sizing that vector using the resize method to be the same as the size of our original vector of integers. And all we're doing is we are returning the increment of each element of the array. And so vi before our transformation is 1 through 10, and vi2 is 2 through 11. So we're just incrementing the numbers and storing them in our destination. This, you can see, could be a very powerful and convenient thing to do. There's another version of this that actually takes 3 ranges, and it allows you to operate on 2 ranges and store your results in a third range. And so here, our third range is actually the same as our second range. So we're taking our first range, which is 1 through 10, and our second range, which is 2 through 11, and we're adding them up and storing them in vi2. So our result is 1 plus 2, 2 plus 3, 3 plus 4, 4 plus 5. You see that? And that's getting stored in vi2. So again, this is very powerful, very flexible. And again, because these are algorithms and they're not actually part of the individual classes, the possibilities open up that you can do with these different algorithms. So finally, a more practical example, I'm using transform to change all the strings in our headline, Big Light in Sky slated to appear in East, and give them initial capital letters. And so here I've got a little lambda expression that actually stores a context value on the outside of the entire function, and it uses it here. And this little variable in the square brackets of the lambda function is called a capture. And so here it's capturing a reference to this variable so that it can actually store things in the variable like that. And if that last is a space, then it goes ahead and it uppercases the next character. Very simple, and the result is right there. After our initial cap transformation, our string now has initial capital letters. So the STL algorithm library is tremendously useful and very powerful. I strongly recommend that you become familiar with all of the algorithms in the library. There's a lot of them, but it's really worth your time. They tend to be flexible, they tend to be efficient, and they may be uniformly applied to a wide variety of containers. Now let's go ahead and bring our screen back to its original configuration, and we'll delete the working file and clean to get set up for the next lesson.